I want to take a look at some algebraic properties of the cross product in relationship to some of the other vector arithmetic that we do. We have noticed that the cross product is not commutative, right? It's sort of anti-commutative. There's also a matter of the associative property, because with dot product we didn't even have an associative property because it didn't make sense to do a dot product of a dot product. Um, but with cross products, you can, if you got three vectors, u, v, and w, you can group them this way and you can group them that way, and it's going to turn out that we actually get different results. Now, I have to admit that I don't ever remember this. I have to look it up every time. But let me show you the gist of what's going on here. Um, if I look at the vectors v and w, these are the ones that are being crossed inside the parentheses, and then I got the u on the outside. So if this is the vector v and this is the vector w, I am using red here, I don't know, but they're in a plane. In fact, I'll draw this plane in red. So they, here's the origin right there, and there's a plane determined by those two vectors. Okay. Now, when I look at the cross product of those two, v crossed with w, it's going to be some vector which is perpendicular to both v and w. So it'll actually be perpendicular to the plane determined by those two. Okay. Now you got vector u out here somewhere. So I've got vector u. I have no idea which way it's pointed, but let's just draw it out here like that. There's vector u. And I want now u crossed with v crossed with w. Well, u crossed with anything is going to be perpendicular to u. But anything crossed with v crossed with w will be perpendicular to v crossed with w. So the next vector I draw has to be perpendicular both to the u vector and to this blue one, which was the cross product of v and w. And maybe I can pick another color. Let's do orange. Okay, so now I got an orange vector that's going to be perpendicular to both of those, and it's coming out here somewhere. Right? It's both perpendicular to that and it's perpendicular to this. In particular, it's perpendicular to this blue one, which was perpendicular to this plane. So the orange vector, which is the result of this triple cross product, is in the plane of v and w, or parallel to the plane of v and w. And so what we have here is that this cross product can be written as a linear combination of the v and w. Notice this is just a number of some kind times v, and this is a number times w, and you're adding them together. So you're taking a linear combination of v and w, which tells me that that cross product is in the plane of v and w. Now when I look at it on this other one over here, u crossed with v crossed with w, the result is going to be perpendicular to this cross product, which means the result is going to be in the plane of u and v. Well, u and v is definitely not the same plane as the plane that v and w described, and so you're not even going to be in the same place unless you end up as vector somewhere parallel to vector v, but that's not at all. I mean, that's going to have to be a very special case that you end up back perpendicular, back parallel to v. So in general, this cross product and that cross product are laying on two different planes, and they're not equal to each other. Okay. Anyway, I understand what they're telling me. The actual, getting the right coefficients here. I just look it up every time if ever I need it. Okay. So anyway, let's come down here and look at these properties. This one we've already seen. There's a distributive property that if you have u crossed with v plus w, then that's u crossed with v plus u crossed with w. Please note this is like matrix multiplication, and that it's not commutative. So if the u here is on the left-hand side, it stays on the left-hand side in each of the cross products over here. Likewise, if the thing you're crossing is on the right-hand side and you're distributing over vector addition here, then this thing stays on the right-hand side. So the u crossed with w, v crossed with w, the w is on the right-hand side. This one here that if you take a cross product and multiply it by a scalar, that's the same as multiplying either one of the vectors by a scalar and then taking the cross product. E, if you cross anything with a zero vector, you're going to get a zero out. And lastly, if you cross any vector with itself, you get the zero vector out. These last three properties here, I see really in terms of taking a determinant. One of the ways we think about calculating cross products is by using a determinant. And this one to me says, you know, if you remember how that determinant went, you do I, J, K, U1, U2, U3, V1, V2, V3, right? You do that thing. Well, this one looks like I'm taking this and multiplying this row by K. Well, what happens to a determinant when you multiply one of the rows of the matrix by K? Well, the result gets multiplied by K. Or if you multiply this one by K, this is a different K. This is the vector K. That's a scalar multiple K. Anyway, multiplying this row by K would give the same effect of multiplying the determinant by K. E right here is saying, hey, if one of these rows is all zeros, I mean, what's the determinant of a matrix that's got a row of zeros? Well, the determinant is 0. So that's where that is. And likewise here, U crossed with itself. If you have two rows that are the same and you take the determinant, then you get a 0 out. This one I also see geometrically in that we've just talked about in the previous video, the length of the cross product is the length of the first vector times the length of the second vector times the sine of the angle in between them. Well, if you're crossing the same vector with itself, the angle in between U and U is 0, and the sine of 0 is 0. So you get a vector of length 0 by crossing a vector with itself. So anyway, there's some algebraic properties of the cross product.